Using lasers in space sounds like a scene picked up directly from a movie, but in reality, it's something that is about to happen anytime now. NASA has taken it upon their shoulders to make the communication between the space missions and the ground stations on Earth more efficient through the use of infrared lasers. The planning period has come to an end, and now it is time to finally implement everything that they have been working towards. So how do these lasers work, and how do they help in communicating to the on-ground team? Stick around to the end to find out. NASA's upcoming Laser Communications Relay demonstration could change how the agency communicates with future missions throughout the solar system. According to the agency, these lasers could result in more high-definition films and images from space than ever before. The mission was launched on December 5th from Cape Canaveral, Florida, as a payload atop the U.S. Department of Defense's Space Test Program Satellite 6. NASA has been using radio waves to communicate with astronauts in space missions since 1958. Despite radio waves having a proven track record, space missions are becoming more sophisticated and collecting more data than ever before. Consider infrared lasers to be the Earth-to-space communication equivalent of high-speed internet like 5G, rather than the painfully sluggish slow-speed internet like 2G. Data will be sent to Earth at 1.2 gigabits per second from a satellite in geosynchronized orbit with the Earth, 22,000 miles above the surface. Now, this is equivalent to downloading an entire movie of, say, 100 gigabytes in under a minute. So, here are 6 things you should know about the new Laser Communications Relay demonstration at NASA. Number 6. LCRD is one of many upcoming laser-based missions. LCRD is definitely the kickstarter to laser-based communication systems that are to be established in space. But they are certainly not the only ones. NASA has a series of these laser communication demonstrators that they plan on establishing in space for a more effective communication. The Terabyte Infrared Delivery CubeSat payload will set a new record for speed in laser communications by transmitting data at 200 gigabits per second. The integrated low Earth orbit user modem and amplifier terminal aboard the space station will be the LCRD's first user. Illuma-T, as it is abbreviated, will deliver a 1.2 gigabits per second data rate to the orbiting laboratory, allowing it to send high-resolution photos and movies of active experiments down to Earth. The Orion Artemis II optical communication system will enable the astronauts aboard the Artemis II who are orbiting the Moon to send high-definition video feed from there to the Earth for smooth communication. Finally, the Psyche mission will arrive at its goal, which is an asteroid 150 million kilometers from Earth, in 2026. Psyche will carry the deep space optical communication payload to test laser communications against the unique challenges of deep space exploration. Number 5. The LCRD will allow the government and commercial partners to test laser capabilities from orbit. From the geosynchronous orbit where the communications between the astronauts and the ground staff occur, which is some 22,000 miles above Earth's surface, the LCRD will demonstrate the viability of laser communication networks. LCRD will spend 2 years conducting tests and experiments before aiding additional missions. OGS-1 and OGS-2 will run transmission tests during this period, transferring data from one station to LCRD and then down to the other. Experiments from NASA, other government organizations, academia, and private enterprises will be used to test laser functionality at the LCRD. Examining effects of air disturbances on laser transmissions and showing trustworthy relay service operations are 2 examples of these experiments. These testings will help the aerospace sector to learn from the LCRD and improve the technology in preparation for future use. NASA is providing these opportunities in order to expand the body of knowledge around laser communication and encourage its operational use. LCRD will enable in-space missions after its trial period, including an optical terminal that will be put on the International Space Station. This terminal will collect data from onboard research experiments and send it to LCRD, where it will be relayed to Earth. Number 4. The LCRD depends on ground stations in California and Hawaii These two stations are primarily the sources of communication between LCRD and Earth. After LCRD receives and encodes data, the payload transmits the information to ground stations on Earth, each of which is equipped with telescopes to receive the laser signal and convert it back to digital data. The optical ground stations, or OGS-1 and 2 of the LCRD, are located on Table Mountain in Southern California and the Haleakala volcano in Maui, Hawaii, respectively. While laser communication can boost data transfer rates, atmospheric disturbances such as clouds and turbulence can cause interference with laser signals. The OGS-1 and OGS-2 locations were chosen for their clear weather and remote high-altitude positions. The majority of the weather in those places occurs below mountain peaks, providing a generally clear sky, which is ideal for laser communications. Number 3. Laser signals are transmitted back and forth with the help of two terminals. The LCRD satellite is a relay with a number of extremely sensitive components that improves communications. LCRD eliminates the necessity for direct line of sight to Earth antenna by acting as a relay. The LCRD has two optical terminals, one which receives data from other satellites or stations and the other of which broadcasts data to Earth-based ground stations. The modems in the LCRD convert digital data into laser signals, which are subsequently communicated by the relay's optical modules through encoded beams of light, which are undetectable to the naked eye. The LCRD can both send and receive data, allowing mission data to flow continuously to and from orbit. LCRD is NASA's first two-way end-to-end optical relay thanks to these characteristics. These are only few of the parts that make up the LCRD payload, which is the size of a king mattress when put together, which is quite small if you consider its purpose. Number 2. Using a single transmission, LCRD will allow spacecrafts to send more data to Earth. If you grew up in the late 1980s or early 1990s, you would recall the slow and painful dial-up speeds of the internet. The addition of laser communications to spacecraft is similar to humanity's adoption of high-speed internet via fiber optic networking, and it is revolutionary. Thanks to our home internet connections, high-definition videos, shows, and content can now reach our screens almost instantly. This is partly due to fiber optic connections passing densely packed laser light through plastic or glass cables, resulting in a speedier user experience. Space-based laser communications, which allows a spacecraft to broadcast high-resolution photos and videos over laser links, uses the same concept. Spacecraft can transmit back more data in a single download now that laser communications are in place. NASA and the aerospace industry are capitalizing on these advancements by developing more laser-based missions to supplement radio frequency satellites. Number 1. LCRD will transform the way NASA gets and sends information from space. NASA has employed radio frequency devices to communicate with astronauts and spacecraft since the beginning of space exploration. However, as more data is generated and collected by space missions, the need for improved communications capabilities grows. LCRD takes advantage of the power of laser communications, which encodes and transmits data to and from Earth using infrared light rather than radio waves.